No, we didn't finish. We didn't finish the last lecture. There was one, I remember, there was one last example missing. Was it important? Let me check. Yeah, there were some join-ins missing. I think we skipped this one for now. We had so many examples, so, and I think everyone wants to hear something new. So let's go to the next chapter. So in this chapter, we will look into solution reactions. So specifically water aqueous solutions. So some components which are dissolved in water. So solutions are examples of mixtures, right? You remember we talked about this classification of matter before, where we had these pure compounds and we had these mixtures, different compounds. So this will be one example of a mixture. And we will also look into the types of chemical reactions we can have in solutions, precipitation reactions, and stoichiometry as always, acid-base reactions, oxidation reduction, and so on. So in fact, I think I wouldn't be wrong saying that almost all chemistry happens in solutions. So of course there is also gas chemistry, there's also chemistry in solids, but most chemistry happens in solutions. So in our body, everywhere. So that's why it's kind of important, this chapter, and it introduces us to many different kinds of chemical reactions which can happen. Okay, so what is water? Water obviously is everywhere in our body. Over 60% of our body consists of water. It affects us not only in terms of our body but also in the earth to keep our earth temperature regulated. In fact, the sea absorbs most of the CO2 that that is produced. So that's actually one of the most very worrying things about climate change, that there is this carbon dioxide loop on our Earth. So the water has to keep that CO2. But what happens if the water becomes warmer? As we will also learn in this lecture, then the solubility will decrease. CO2 will be released to the atmosphere, and this is actually a much more significant amount than what we produce as a human. So there's kind of a death cycle, right? So we produce CO2, we warm up the sea just a little bit, but that little bit releases a lot of more CO2, and so it's a cycle that we cannot stop at some point. So that's probably what I'm most worried about climate change, that we already are over this tipping point, that at some point that we cannot stop this anymore. Okay, but this is a side quest, so yeah. So how does so what does water actually do, and how does it look like? So we have this banded molecule, right? An oxygen atom and two hydrogen atoms. And well, you could ask the question, why is it actually bent at 105 degrees? Why is it not just linear, right? And that's something we will answer later in this lecture. It has to do something with where the electrons actually sit and how they form these bonds. In general, what this kind of specific geometry has a big influence on the chemistry of water. So first of all, what you can realize when looking at the periodic table is that hydrogen often wants to give away an electron, while oxygen wants to get 2 electrons, right? It wants to become noble. We always said all elements want to become noble, almost all of them, at least the non-metals. So we expect that the oxygen will have some kind of like partial charge, right, assigned to it. So we usually indicate it like this. So this just indicates that the oxygen has a tendency to pull these electrons from the shared bonds here. So to pull these electrons here to the oxygen. Just because we know that the oxygen wants to like get more electrons to become noble, right? And it has to, in principle, get 2 more electrons to become noble. Right? And this actually leads to a so-called dipole movement. The dipole moment just means that we have a separation of plus and minus, right? And so this means that if we, for example, have some electric field with plus and minus, then the water will move in that electric field, orient. So this is actually an important property of water, so which fully comes from its geometry, right? If it would be linear, we wouldn't have any dipole moment. We will talk about this also later more. And the fact that we have here this distribution and separation of charge means we have a so-called polar bond, where we have the electrons not equally distributed between the atoms. You just imagine something like a hydrogen molecule. In this case, the electrons are exactly equally shared between the 2 atoms. So this bond here would be non-polar. So a polar bond is a bond where we have a separation of charge to the 2 atoms. So one of the atoms prefers to have the electron, the other one prefers to give them away. Yeah. And this polar bonding of water and the corresponding dipole moment is actually one reason why it is a very good solvent. So it can take some molecules and it can put them into solution and surround them. So this process is actually called hydration. So if we just imagine some molecule, maybe like HCl. HCl. So HCl has here the negative side, here the positive side. This is not good. So again, chloride likes to get 1 more electron, right? H likes to give it away. If this becomes more serious, then the chloride might completely dissociate from the proton, right? As we know, then the chloride can even form some, just an ion, not a molecule. For the moment, let's just keep this as a molecule. Then what will happen with the water? Well, the water has a positive end here, which is the protons. And they will obviously like to coordinate with the negative side. Right? So the water will kind of coordinate with the chloride. And on the other side, we have this positive one here, which will somehow coordinate with the negative oxygen. Right? So this process is called hydration, and if this goes on, then eventually you might fully dissociate this. I just draw the water like this. Not a good idea. Right, it might fully dissociate into a proton and a chloride. I just draw some random number of water molecules here, right? So water can dissolve polar molecules, right? And it can even dissociate them if the water has a strong coordination with some of the atoms. Okay, and this is exactly also what happens when we dissolve salts. So salts, for example, sodium chloride. We drew this like this. So there's this periodic lattice of the atoms, as you remember, which repeats until almost infinity on macroscopic dimension. And what happens if we add water to this? Well, then some of the ions, so in this case, chloride would be the large ion, be surrounded by the water, and the sodium will be also surrounded by the water in the other direction. Right? So we will form dissolved ions. So if we write this as a chemical equation, we would then write this like this. So you can see this was a solid before. Now the ions are dissolved in water, so we put AQ for aqueous, for dissolved in water. Yeah, so that we don't put the water here explicitly. Why don't we put the water in the chemical equation? Because typically we don't know how many water it binds to. Like, there are experiments that we can use to determine how many water are actually coordinated here, but it's kind of like a continuous transition. So water is a liquid, right? So maybe there will be another shell of water and another shell of water, and they may be like very dynamically changing their positions. So it's difficult to define like a unit, like this is my molecule, right? That's why we just use this index AQ to indicate that this is in water. We don't exactly know how many water there are. On average, there will be a certain number, but just to avoid this kind of confusion, we just put AQ. Okay. So this is this process, a bit nicer drawn than what I just did. Sodium chloride crystal, the water comes to the ions, it coordinates with the respective side, negative or positive side, and it makes these hydrated ions. So if you look into any kind of solutions, these ions will typically be hydrated. That's because the interactions between water molecules and ions are actually really strong. And I think sometimes we underestimate these interactions. They form really quite stable complexes, almost like a molecular complex moving through the solution. So if you talk about ions, like moving around, in the solutions, they don't move as an atom or an ion. They always move with their hydration shell around. Okay. So this is what I just said. So we typically write this one as an AQ. So we get a dissociation of salts into the cations and the anions. And then the question you could ask is, what determines if my solid will get dissolved in water, right? Maybe you have experienced putting different things into water, and maybe some of them were dissolved, some of them were not dissolved, right? So the question is, like, what determines the differences? So one example is sodium chloride, which is very soluble, but silver chloride is not soluble at all. So now you could think why? Because they look very similar, right? Silver chloride, you just replace the sodium with silver plus. Seems almost the same thing, but solubility is very different. So what does the solubility depend on? So, and now we have to really look at this equation, what we are doing here. You can imagine that we are doing like a two-step process. First, we take this crystal and we break this apart into ions. Let's just put them into the gas phase. And then the next step is we solvate them with water, right? So we can kind of imagine this as a two-step process. At first we have to break up these bonds, these ionic bonds between sodium and chloride ions. And as a second step we solvate them. Now the first step will take us a lot of energy, right? Because we have these strong ionic bonds. They don't want to be dissociated. They will hold this. But then when we go to step here, then we gain back a lot of energy. So you can kind of imagine this as climbing up a hill, but then rolling down again when we hydrate the ions. And the question is, eventually, where do we end up? Like higher or lower than before? Right? So that is the essential question, and that is what determines the solubility. So kind of we are starting here, we go up here, this would be the gas phase, and this would be the final state. And this would be the ionic bond energy in the solid. And this would be the hydration energy, right? So if this resulting difference here, if this is smaller than 0, then we can say that it is soluble. Because in the end, we are able to move down in the energy, right? Which is always good. We'll talk about this more later, but essentially that's a simplified way of saying it. Well, if we would move up in energy, but we would not gain much hydration energy, then it must be like a larger 0, and it's not soluble. So this picture is simply based on energies, and it turns out it's not exactly right, because it doesn't consider one important thing that matters, which is entropy. We will talk about that later in this lecture. But this is one part of the game. So in the end, we will realize that energy is one driver of solubility, energy. And the other driver of a chemical reaction or solution process would be entropy. And we will introduce this later. This has to do something with the order. It has to do something with a tendency in nature that everything wants to spread out. Energy wants to spread out. It doesn't want to be like localized. So that's why things tend to become disordered over time. So in this specific case, you can imagine this has a high order, this has maybe low order, because these ions are just running around in solution. But at the same time, the water is also losing its disorder. It's becoming more structured around these ions. So it's a bit difficult to talk about solubility because it's a function of all these things. But energy-wise, you can think about it as a balance between the energy to split the bond and to hydrate it. And eventually, there will be also some entropic contributions, but we will not talk about this here yet. Okay, and water can not only dissolve ionic substances, it can also dissolve polar molecules, for example, ethanol. Ethanol has this OH group, so this is ethanol. It says carbon atom with 3 hydrogen, carbon bond, and then there's an OH bond. And the O, we know already, has always a tendency to get electrons, while the H can give it freely, so we have a polar bond. And once we have a polar bond, it can interact with the water molecule, right? Which means that we can actually put this into solution and it can dissolve. So what would happen if we would like increase this carbon chain? We go to like maybe C10 or something like that. Then we will realize that we will reduce the fraction of this polar bond, and the molecule becomes much more unpolar. And eventually, we have oil, and we separate oil and water, right? So why do oil and water not mix, right? That's the question you should ask, right? If we put oil into water, why does it not mix? Well, there's a simple reason for that. Water already has other water molecules around it. It makes some nice stable bonds, right? They have these dipoles. The dipoles interact with another dipole. Negative and positive end will come to each other. They like each other, right? But then there comes this other molecule, which is not polar. Then why should the water, if you think from the perspective of the water, why should it actually leave its friends and go to another molecule which doesn't even make any stable bond, right? So that's the reason, and that's why we usually have a concept which we call like dissolves like. So if we want to dissolve a polar molecule, we need a polar solvent. And if we want to dissolve a molecule which is not polar, we need a non-polar solvent. Let me just write this here. Second. So, for example, polar solvent dissolves a polar molecule. Or non-polar solvent dissolves a non-polar molecule, right? So the reason is simply that there are these strong interactions between polar molecules. So you don't want to really like break them apart. You don't want to. The water doesn't like to leave its friends for something which is non-polar, right? But ethanol is a pretty good other friend that it could leave the partner because ethanol has this polar side chain, so it can make also some strong interactions. So it's okay to leave his friends, right? Okay, so that's basically like dissolves like principle. Mm-hmm. Okay, so these are solutions, right? Solutions always consist of a solvent and a solute. The solvent is the substance which is in excess, which will bring the solute into solution, so which will basically take him away from its friends, like let's say sodium chloride. It has its friends there, all the sodium and chloride ions. But the solvent comes in and it will break it apart and it will take it and put it into its coordination environment, right? That's what the solvent is doing. And the solute is getting kind of dissolved in that solvent. And they will form eventually a homogeneous mixture, meaning that there's just one thermodynamic phase, which is the liquid phase. Now, once you have these ions in the solution and you apply some voltage over it, then the solution can also conduct current. Pure water itself is not really electrically conducting because there are no ions in water. It will have a very small conductivity due to these dipoles moving, but it's like very, very small compared to actual ionic solutions. So ionic solutions is what we call usually electrolytes. So these are solutions which have ions dissolved in it so that they can conduct electricity. So this shows the electric conductivity of different aqueous solutions. So on the left side you see an ionic solution which has a high ionic concentration. And you can see the lamp is pretty bright. Once we decrease the concentrations of ions, you see the lamp is not really lightning at all. And once we have no ions at all, then the light is just turned off and there is no conduction. of any current anymore. And then what we usually also distinguish is strong electrolytes. So strong electrolytes are the ones that can effectively conduct a current. For example, sodium chloride. Why do they effectively conduct a current? Because they dissociate almost 100% in water. They have a high solubility. Yeah? If you put sodium chloride into water, you are very well used to that when you do cooking, and it will completely like dissociate into ions. There's nothing remaining. And then there are also weak electrolytes. These are like usually molecular electrolytes, like acetic acid. They will partially dissociate in the solution. So acetic acid. Acetic acid looks like this, and in solution, so this would be, for example, a liquid, and then in solution, this would go into one proton would actually dissociate, and we will learn later in this lecture that this is an example of an acid-base reaction. So the oxygen again has a tendency to pull away the electron from the hydrogen, and it turns out that in this case of acetic acid this can happen to a certain degree, but in solution you will actually have both. You will have this one and this one. This dissociation is not complete. Right? So that's why we call this a weak electrolyte. So in other words, like in the solution, you will have like a couple of acetic acid molecules and a couple of acetate ions. So this one is here acetate, and this one is acetic acid. Yeah. That's why we call this a weak electrolyte. So they will obviously then conduct a smaller current simply because we have less ions per molecule, right? And then there are also non-electrolytes. These are the ones who don't dissociate at all into ions, like sugar. So they will not give you any kind of significant current. So it was by Svante Arrhenius who actually then correctly identified the basis for conductivity properties of solution. And what he postulated was the extent to which a solution can conduct a current depends only on the number of ions which are in the solution. Yeah, so that means that the more salt molecules you put in the solution which can dissociate, so the more dissociation you have, the higher the conductivity will be. And that also means that if you have a molecule which can dissociate into 2 or 3 or 4, the more ions it can dissociate to, the higher the conductivity will be per molecule, right? Okay, so let's go through some examples here for the strong electrolytes first. These are, as I said, substances which are completely ionized, high solubility, they will completely dissociate. And one example is salts, sodium chloride, as we just discussed it before. Another example is strong acids. So one of the strong acids is actually HCl. So when you put HCl in solution, it will almost entirely split into protons and chloride anions, or nitric acid or sulfuric acid. All of these are strong acids, strong electrolytes, because they have dissociation reactions where they lose a proton, and they can therefore produce ions which can conduct a current. There's also so how this acid actually works is that it's kind of annoying. Why this happens actually? I'm always wondering about this. Let me try the other one. think the cable is